Okay. So, today we discuss some important concepts like mean and variance. Now, we are given a random variable x and its probability density function is p x. X for the time being is continuous random variable. Then we define its mean mu x as also expected value, it is an operator. E actually means expectation, it is an operator, it is just a question of notation, expected value of x as okay. Now, you can how this formula comes, maybe we can give a frequency interpretation. Suppose in the discrete case, suppose x takes some values like x 1 or x 2 up to say x p. This is n 1 times of if you observe x, maybe on n 1 occasion you get x 1, on n 2 occasion you get x 2 dot 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 dot, on n p occasion you get x p. So, what is the arithmetic average? Net value is summation n I x I divided by summation n I. This is the total number of trials. Okay. If you can call this as capital N. In that case, what you have is this n 1 by n x 1 plus n 2 by n x 2 plus dot 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 plus n p by n x p, right. Now, what is n 1 by n? If out of a trial of very large number of trials equal to capital N, if on n 1 occasion you get x 1, n 1 by capital N, as you have seen earlier, it approximates the probability of x taking the value x 1. So, you are multiplying x 1 by its probability. Similarly, you are multiplying x 2 by its probability and so on and so forth, and you are adding. Okay. So, this was for the discrete case, but you can easily extend this concept to the continuous case. There this summation becomes a continuous summation, which is nothing but the integral, and instead of the discrete probabilities you put the continuous probability function, that is the probability density function. So, you get p x x dx or x p x dx integral over the range of x, which is in the most general case from minus infinity to infinity. Okay. So, it gives you the average, we call it statistical average or mean or expected value of the random variable x. Take an example. Suppose x is uniformly distributed, x uniformly distributed. This is an example. Maybe there are two values x 2, x 1. Uniformly distributed means within this range it has a constant probability, and outside this range its probability is 0, right. Since the total probability has to be equal to 1, if this width is x 2 minus x 1, the area has to be 1. So, this is height will be 1 by x 2 minus x 1. Okay. So, in this case what is mu x? Mu x is x into 1 by x 2 minus x 1, this is a probability density function, times dx, and x is varying over the range from x 1 to x 2. This is constant, you can take it out. Okay. So, it becomes x 2 minus x 1. If you integrate x, you get x square by 2. So, x square by 2 from x 2 to x 1. So, x 2 square minus x 1 square, you factorize, one factor cancels from top and bottom, and finally, you get this quantity. X 2 plus x 1. So, just the average of these two values x 1 plus x 2. So, if it so happens that x 2 is on this side and x 1 is on this side and they have the same value, same magnitude, then the mean will be origin. That is, if x 2 and x 1, if x 2 equal to minus x 1 or x 1 equal to minus x 2, obviously this will be 0. Okay. Otherwise, the mean is at the center point between x 1 and x 2. Okay. This for uniform, you can try with other cases also. Well, we gave the formula for mean for a continuous random variable, but we can easily extend it to the discrete case. Okay. In the case of discrete random variable x, x will take either some value x 1 or x 2 or x 3 like that, some discrete values, not continuous values. Okay. And for each value you have got some probability density function. So, for a discrete case, if x is discrete, then p x is nothing but, this we have seen already, p I delta x minus x I. So, x can take either value x 1, okay. Then the probability density has an impulse with strength p 1, or x can take x 2. So, probability density is an impulse there with strength p 2 and likewise. So, I am summing it over the range I. So, for various discrete values of I mean we have got impulses. So, x can take one of those discrete values, right. In this case, obviously mu x is nothing but as before x p x dx from minus infinity to infinity. You substitute p of x by this, but as you know, if you do this integral, any integral x delta x minus say x I dx minus infinity to infinity, what you get is x, this integral becomes x I. This standard result, the impulse has 0 value everywhere except at x equal to x I, where it is actually pointing to infinity, but the integral will be 1. Using that concept, actually this is a fairly established result in signal theory. So, you can as well look into those books on signal system, this is given clearly there. This integral is x I. So, if you really make use of it, substitute p of x by this expression here and sum it up, you get simply this value p I x I, okay, which means suppose x takes these values either 1 or 2 dot 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 up to 6 values, okay, and each has probability p I equal to say 1 by 6, I equal to 1, 2 up to 6. That is probability of x taking value 1 by 6, probability of x taking value 2 is again 1 by 6, so on and so forth. What is E of x then? Simply p I x I equal to 1 to 6, but p I is common for all of them 1 by 6, which I can take out x I, that is 1 plus 2 plus dot 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 plus 6 . Okay, how much is this? This is equal to 3.5. Okay. Yes. So, this is the mean. Okay. Then we can again extend this case further to the conditional mean. Okay. That is, suppose there is an event, there is some event m m an event. Now, subject to the condition that means event m has occurred, what is the mean of the random variable x? Okay. So, previously it was unconstrained, there was no constraint like this, but now there is a constraint that we are saying that there is an event m that has occurred. Subject to this constraint, what is the expected value of x? Obviously, in such case we should write like this, it is nothing but sorry is nothing but x simple. This is a conditional probability density. Okay. And in the discrete case, very simple. Here x is a continuous random variable. So, we have an integral and probability density function. There x takes only discrete values. So, we have got a summation, discrete summation, okay, and x I summation over I, okay, and the probability of x taking x I subject to m. Okay, these are discrete probabilities. This summation multiplying by the this discrete probability multiplies the corresponding discrete value of x, and you sum over all the possibilities of these discrete values. So, sum over I. Okay. As an example, suppose x continuous random variable, and given that event m is nothing but x taking values greater than equal to a. So, x is constrained to take values greater than equal to some number a. Subject to this constraint, what is the mean of x? Physically, it means that we are observing x, but in our observation we are not considering all possibilities of x, we are only counting those cases where x takes numerical value greater than equal to a, and out of those observations what will be the mean expected value of x. Okay. So, that means as before, this is a general formula first I am writing, sorry. Okay. Now, what is p x by m here? That is p x by this incident. What is this? We know that this can be written as p x divided by this. This is a probability density of x divided by probability density of the probability of x taking value greater than equal to a. Okay. This is the probability of x taking value greater than or equal to a. Okay. The event x greater than or equal to has this probability, right. So, this is the probability of x taking value greater than or equal to a. We divide the probability density of x by this and we get that. Okay. So, in this case what is then it turns out to be x, this probability p x dx, and this is a constant. This is a probability of net probability of x taking value greater than or equal to a. So, this will go in the denominator, and here x now takes value not about the entire range, but from a to infinity, right. Okay. And what is this quantity? This is also the total probability of x taking value from a to infinity. Okay. So, this will be the conditional mean of x. Okay. Now, we come to an interesting topic which is little trickier than this. That suppose x is a random variable and a function is given. So, I am not considering the random variable as such, but I am considering another random variable y which is related to x by a function g. It is a continuous function g of x. Question is, what is the mean of y? What is the mean of y? Now, by the previous discussion, just a minute. By the previous discussion, we can always say that this will be given by y p y. I just put a subscript y here. Okay. So, and to indicate that this is actually the probability density for the random variable y, it takes the value y. Okay. This is the random variable and this is the value, and as long as we have got two random variables x and y, I will reserve this for the probability density for the random variable of x. X is the variable, this is the value. Okay. This way we will be able to differentiate between the two. This is one function, this is one function, they are not same. Now, coming back to this will be the mean, but that means that suggests that in order to calculate this mean, first we have to find out this probability density function, which could be cumbersome. Is it necessary? Answer is no. We can show that this is actually given by, this will be same as identical to the expected value of g x, that is which we also called expected value of g of x. G of x and y are same, so it is the expected value of g of x. This can be shown. It is not difficult, so let us take it up. Okay. Just consider a general kind of g of x. For the time being, say I am having this is my y, and this is y plus dy. This point could be x 1 and this is dx 1, this point is x 2 and this distance is dx 2, this point is x 3, this is the x axis of course, and this distance is dx 3. Okay. So, in such a case, what is the probability of y taking value between y and y plus dy, that is what is the probability of y falling in this range? That is same as the probability of x falling in this range, in this range and in this range, right. Now, what is the probability of x falling in this range? That is, since it is very thin, infinitely small, this is probability density function at this value, that is at x equal to x 1 multiplied by this. That means, this is the probability of y falling in this range between y to y plus dy. This will be equal to first P x x 1 dx 1 plus P x this will be the probability of x falling within this range, this will be the probability of x falling within this range, like that. Okay. And you can easily see one more thing, y is same as g of x 1 or g of x 2 or g of x 3. Okay. So, if I multiply this side by y, okay, if I multiply this side by y, this side also I multiply by y, but y is this, y is this, y is this, right, y is g x 1, y is g x 2, y is g x 3. So, this while multiplying this I multiplied by g of x 1, while multiplying this I multiply by g of x 2, and while multiplying this I multiplied by g of x 3. They all are same equal to y. Okay. Now, actually here I have to now integrate over the entire range of y, which means I have to now integrate here. Okay. Now, as you see, this is very interesting. As I integrate, as this strip between y and y plus dy, as this strip increases, okay, becomes wider and wider, what is happening? This also x 2, this is moving to this side, this tip is moving to this side, and in this case, suppose I hold y for the time being, hold y here and pull it up, pull this y plus dy up. Okay. In that case, this point will be going towards this side, and this point will be going towards this side, and ultimately when y is here, that time they will meet here. Okay. And as y goes up further, on this side we will not have anything, okay. It will come from this side. And now suppose y is pulled down. Of course, as y goes up, as I expand this, on this side also this segment widens, and as y goes up further and further, on this side, on this left hand side there is no intersection anymore. So, contribution comes only from this side as I go above. This goes on widening. If y plus dy is here, I will have larger section here. If it goes up further up, I will have still further area, and like that. And as y is pulled down, when it comes to this minimum point, as it is pulled down, this x 3 moves leftward, x 2 moves rightward, and at this point they are meeting together, right. And as y goes below that, then contribution comes only from the left hand side. So, actually the integrals are non-overlapping, okay. And as I pull y from minus infinity to infinity, those three integrals, they are mutually exclusive, but they cover the entire x axis. Okay, they cover the entire x axis. In that case, integral will be same as, if I do this integral, this will be nothing but g x p x dx over the entire range, because this will give rise to one integral, this integral. Their domains are mutually exclusive, as you are saying, and as y is pulled from minus infinity to infinity, we get three distinct domains, one from this side, okay, but they are non-overlapping, but they are cover the entire x axis. Okay. So, all of them we put under one integral, and we can write like this. I am writing the same formula again in the next page. So, if in conclusion, if y is given as g of x, then E y, which also can be written as E g x, is equal to this is a very useful and interesting result. It is widely used, dx. Okay. This was for the continuous case. So, if x is discrete, you can easily extend this to the discrete case. That is, suppose some consider the discrete case now. So, this function is given again, okay, but x, unlike here, x is taking values, discrete values, either x 1 or maybe x 2 or maybe x 3 and like that, okay, and each has its own probability. So, we have got in this case p x is nothing but p I delta x minus x I, standard case. Okay. So, x can be x 1 or x 2 or x 3, whatever, these are the discrete values it takes. In this case, if I define a random variable y as a function of x, I mean as a function g x, then what is the probability, what is the mean of y? You can easily get that from this concept. In this case, E y will be what? Here we had a continuous summation, now it will be a discrete summation over I. Okay. And then this function and x will take values x I could be 1, I could be 2, I could be 3, okay, and each will be multiplied by the corresponding probability x taking x I. That will be the mean of y, or equivalently you can write E of g x. Okay. Let us consider an example. Suppose g of x is given like this. Its value is 1 up to some number, say a. To the left of a, its value is 1, to the right of a, its value is 0. So, x is a random variable and I define y as g x. So, y is another random variable, in fact, it takes only 2 values, either 1 or 0, and the way it takes these values is given by this function. So, what is the mean of y here? Same as, I use the same formula, g x multiplied by p x. I am dropping the subscript x here now, because again I have got only one random variable. So, I can as well drop it without any confusion, this. Okay. But g x is 1 up to this and then 0. So, the integral simply becomes this minus infinity to a, and then the value is 1 p x d x. And all of you can remember, this is nothing but the probability distribution. Probability distribution means the total probability of x taking values less than or equal to a. That is, x taking values from minus infinity up to a. What is the total probability? That is called the probability distribution function, right. So, this is an interesting thing. It shows that any probability distribution function also can be shown as a expected value. This is a probability distribution function, but it can always be shown as a expected value by constructing a function like this. Okay. One more example you can take. Another example, suppose there is an event M. Okay. So, if x belongs to M, that is, if so happens that you observe x, okay, and it is a member of M, then x takes the value. If x this, then x takes the value 1. Otherwise, that is, if x is a member of M bar, then x is 0. In this case, what is the expected value? It is a discrete case, x takes value either 1 or 0. So, mean value will be 1 into the corresponding probability p of m and 0 into the probability p of m bar, which is p of m. This shows that a probability also can be shown as an expected value by a construction like this. Okay. Now, we consider some properties of this expected value. we can see one thing, that suppose we have got several functions, that is y 1 as g 1 x, g 1 is one function, y 2 as g 2 x, dot dot dot, y p as g p x. Okay. Instead of having just one function, suppose I construct a linear combination, okay, C 1 g 1 x plus C 2 g 2 x plus dot 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 C p g p x. What is the expected value of this? Obviously, the whole thing will be multiplied by the probability density p of x, multiplied by dx, then integrated. But integral is linear, so the entire integral can be broken down into p separate integrals, one involving this, another involving this, dot 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 dot, another involving this. Integral involving this will give rise to the expected value of g 1 x or y 1, this will give rise to the expected value of g 2 x or y 2, so on and so forth. So, expected value of such a thing will be nothing but okay. So, this is a linearity property. So, the expectation operator actually is a linear operator. If it works on a linear combination like this, then it can be applied to each of them separately and the various results can be just combined like this. Okay. So, expectation operator is a linear operator, this is a very useful result, it will be used many times in future. Okay. Another thing you see, if y is given as say a x plus b, what is E of y? This will be nothing but okay. First term a will go out, you will get a times x p x dx, which is nothing but expected value of x, and the second term b will go out, integral p x dx, which is equal to 1. So, you get b. So, for a x plus b expected value, this expected value of a x plus b is nothing but a times expected value of x plus b. This also is a very useful result, though it may appear to be a simple one. These are very useful results. Now, I consider a complex valued random variable. Okay. A complex valued random variable. Suppose z is a complex valued random variable. It has got two components, one real part, another imaginary part. Say x plus j y. Okay. Then we define the mean of z as mean of x or expected value of x plus j times expected value of y. That is, both x and y, they are real valued. X has its own probability density function, y has its own probability density function. To calculate this, multiply x by p x dx, integrate. To calculate this by this, multiply y by p y dy and integrate. Okay. Likewise, this is the definition. Now, suppose we have got a complex valued function g x, okay, a complex valued function g x, which has got two components, the real part is g 1 x, imaginary part is j times, say this is the imaginary part g 2 x. So, total value is g 1 x plus g 2 x. You can, if you call it y, this you can call as y 1, this you can call as y 2. So, by this definition, what is the expected value of y? There is nothing but e of y 1 plus j into e of y 2. But what is e of y 1? We have already seen that e of y 1 is nothing but g 1 x p x dx, okay, integral. And what is e of y 2? There is nothing but, as you have seen little while back, g 2 x multiplied by p x dx integral, okay, which means e of g x plus j and now you can combine the two integral. So, essentially g 1 x plus j g 2 x together, again you get back g x, same as before. So, whether g of x is a real valued function or a complex value function, expected value of g x is given by this. Okay, the expression is same. Okay. This takes us to a very important concept, that is variance. Suppose x is a random variable and it has a mean mu. So, when you try to measure, when you try to observe x, it is not that always you will get mu, you will get sometimes values above mu, sometimes below mu. So, essentially a question arises, how much is the spread, average spread of the variable x around the mean, or how much approximately is the range of variation, range of fluctuation, okay, around the mean. Does this random variable vary within a small range around mean? Then its spread is less. Does it vary widely around the mean? Then its spread is more. Okay, how to measure this? How to have a quantitative description of the spread? That is given by variance. Okay. So, x random variable R v, mu here is e of x, then you find out this quantity first. Definitely this gives you the spread, this gives you the deviation around the mean. So, in our first attempt we might try to take the expected value of this, because x can take various values depending on each value you get some value for this deviation, sometimes high, sometimes less. So, you may try to get an expected value of this by multiplying by this by p of x dx and integrating. That would give you, in your opinion, I mean that could give you an idea of the average value of the deviation. But the problem there is, even though there is deviation, this can be positive and negative, and your average value could turn out to be 0 or very small, and that will imply as if the spread is indeed very small. But that is not the case actually, because spread still could be very large, but x can take values uniformly to the right of mu, to the left of mu. Okay, so, x minus mu sometimes taking positive values, even high positive values, x minus mu taking sometimes negative values, in fact highly negative values. But if you just keep x minus mu and average out, that average could still be 0 or very close to 0. Okay, and an error, an erroneous implication will come up. I mean, we will tend to think as if this random variable x is fluctuating in a very small range around the mean, but that is not really the case. Here the problem is coming because the positive deviation and negative deviations, they may cancel out and giving an indication as if the expected value of the deviation is 0 or very small. So, to avoid that, we take the square. Sometimes it is called power also, because the point I mean, if you use electrical engineering analogy, mean means DC, x minus mu means the AC, square of that, so power. Okay. And this quantity, whether this deviation is positive or negative, this quantity will always be positive, right. So, if you take the expected value of that, that will give us a correct picture of the extent of the fluctuation, the range of fluctuation or the spread, S-P-R-E-A-D, spread, average spread around the mean. Okay. So, we take this multiply by, so this is a g x here now, function g x. What is the expected value of this? This multiplied by p x dx. Okay. This we call sigma square. The sigma square altogether is the symbol, and sigma then is the square root of this, which is called actually the standard deviation. Okay, standard deviation. So, sigma square is the variance, let us take an example. X uniformly distributed. To make life simple, I assume that the distribution is given like this, capital A minus capital A, which means this is 1 by 2 A. The height is 1 by 2 A, then only the area is 1. What is the variance? First, what is mu? I mean, I do not have to recalculate, you can easily understand that mean will be, mu will be 0. You can easily understand that mean will be 0, right. And what is then sigma square? Sigma square will be E of x minus mean, which is 0 whole square, that is E of x square. And we know the probability density, which is a constant 1 by 2 A. So, you have x square into 1 by 2 A, that comes out minus infinity, sorry, not minus infinity, I mean this will be from minus A to A dx, and this integral is x cube by 3. So, x cube by 3 A minus A divided by twice A. What is this? 2 A cube by 3 twice A cube by 3 divided by 2 A. So, essentially this turns out to be A square by 3. This is the result. Okay. Another very important class of random variables are is the Gaussian random variable. RV for random variable. Here P of x is given by this formula sigma okay. For this function mean, that is E of x will be given by this parameter mu, okay, and variance, that is E of x minus mu whole square is actually given by sigma square. Okay. I just give you an exercise and then I call off today. Suppose I consider, so this is an exercise. I consider a Poisson random variable, Poisson distributed random variable, where the probability of x taking a value k is given by, let me see, e to the power minus a to the power k divided by factorial k. Okay. A is a parameter. And k can be 0, 1 dot 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 like that. Okay. For this, find out okay. So, that is all for today. Okay. In the next class, we will take it up. Thank you very much. Okay. In the last class, we gave a problem. I mean, we said that x is a random variable which is Poisson distributed and it takes values, it is a discrete random variable. It takes values like x equal to either 0 or 1 or 2 dot 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 dot. Okay. And the corresponding probabilities is given by like p, if p equal to, I mean for x equal to k, the corresponding probability will be given by e to the power minus a and a to the power k divided by factorial k, where a is a parameter. We ask you to find out the mean and variance, okay, or rather we ask you to find out E of x, expected value of x, and expected value of x square. Okay, and if you know expected value of x square and if you know the mean, obviously you can find out the variance. Okay, that was the question. A is called a parameter, so we say that x is a Poisson distributed random variable with parameter a. Okay, can you tell us what is the function of this factor e to the power minus a? Actually, if you just consider this part e to the power k by factorial k, okay, this will correspond for various k's. If you take their values and add them, this gives rise to an exponential series. In fact, we should have this thing. This must be equal to 1, right, because total probability is 1. Now, because of this factor, this equality will be satisfied. This we can see easily. Okay. If you put that expression, take this out, k equal to 0 to infinity, and you have got a to the power k divided by factorial k. Now, this is nothing but e to the power a. This is the exponential series. E to the power a when expanded gives you this. So, you have e to the power minus a into e to the power a is equal to 1. So, just to make this equal to 1, this factor has been added, right, introduced. Anyway, this is just a side issue. We have to now find out the mean of x, that is E of x and E of x square. Okay. To do that, we consider this exponential series. E to the power a, which I have just a while back stated, is equal to a to the power k divided by factorial k, k is 0 to infinity, okay, which is equal to 1 plus a square by factorial 2 plus dot 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 plus a to the power k by factorial k plus dot 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 dot, right. I now differentiate these left hand side and also right hand side with respect to a once, and then again one more time, that is twice. So, first if I differentiate LHS, the very next thing from here is a very important thing called characteristic functions. It is basically related to Fourier transform. Fourier transform of a probability density function is actually a characteristic function. Okay. Now, that I will not start now, but I am just telling a little bit about it. Since Fourier transforms have been very effectively used for carrying out convolution and all that, okay, I mean you can use this result in the end, where suppose you have got a summation of various random variables, each having its own probability density, and you have to find out the probability density of the, I mean resulting sum, which is also a random variable. There this characteristic function, I mean is very useful. Also this characteristic function can be used very effectively to calculate moments. The moments which we have just considered, they can be calculated from these characteristic functions very easily. Okay. So, I reserve this for the next class and I stop here today. Okay. So, we have so far covered in this chapter function of random variable, and if y is g x and giving the probability density of x, what is the probability density of y? We took several examples. Okay. Then we went into moments, we went into another important thing, that is given a function g x. What is expected value of g x? That is nothing but g x into p x dx integral. Okay. We consider several examples and applications of that. That took us to this notion of moments, not only mean and variance to start with, but more general case of moments. Okay. And from moments we go to characteristic function. That will complete this chapter. Then we will go into what is called joint statistics, that is not only one random variable, but more than one random variable, say two random variables are present and they are related. So, we will be considering things like joint probability density and all that, and do similar exercise. Okay. So, that so today we stop here. In the next class, as I said, we will consider these characteristic functions. Thank you.